Hello friends, I welcome you in lecture number 20 on relations. In this lecture we are going to discuss composition of binary relations or composition of relations. We have discussed about composition operation for functions. If you recall, if we have two functions say f and g, then composition of f is denoted by GOF, and we have discussed how composition of functions is defined in the lecture series or playlist of functions. So here also we are going to discuss that composition operation for two relations. We will discuss how composition of two binary relations is defined. So suppose we have a relation R from x to y. Suppose R is a subset of x cross y. This means R is a relation from set x to set y. And suppose we have another relation, say S from set y to set z. That is, S is a subset of y cross z. Here to define composition we require two sets. We require three sets, say x, y and z. And suppose R is a relation from x to y and S is a relation from y to z. Then composition of R and S is also a binary relation, and it is denoted by this notation R composite S, and it is a subset of x cross z. If R is a subset of x cross y and S is a subset of y cross z, then composite of R and S is a subset of x cross z, or composite of R and S is a relation from x to z. And here if R is a relation from x to y, then ordered pair xy is in R for x belongs to capital X and y belongs to capital Y. And here elements will look like this. Order pair yz belongs to S, where y belongs to capital Y and z belongs to capital Z. And we are considering R composite S as a relation from x to z. So here order pair xz is in R composite S. Now order pair xz is in composite R composite S if there exists some element y in a set capital Y such that xy belongs to R and yz belongs to S. This is how composite relation is defined. If we want to write down the definition of composite of R and S, then it is subset of x cross z. So its element are in this form. Ordered pair xz belongs to x cross z such that there exists some y in capital Y such that this order pair xy is a member of relation R and order pair yz is a member of relation capital S. If there exists some y in capital Y such that xy belongs to R and yz belongs to S, then this order pair xz is a member of R composite S. This is how composite of two binary relations is defined. Now we are using this notation for composition of two relations R and S, and some authors are using another notation also. Instead of writing composition as R composite S, some authors are using S composite R as the notation of composition of relations R and S. Some books are using this notation and some books are using this notation also. So both notations are valid. but here meaning will change. If I am using this definition and I use this notation R composite S, then here I have this definition. But if I am writing S composite R, then here this will change. So we will get another ordered pair in the form Z comma X. So be careful, whatever text your college or university is using, you have to follow that notation. And if you are not sure, if there are many colleges in your university and if you are not sure that all the colleges are using same notation, then in the examination if they ask you to find out composition of two relations, then you can find out R composite S as well as S composite R. They will find out whatever notation is appropriate for their course. So this is main thing about the notation of composition of two binary operations. Some authors are using R composite S, if you are referring this book K.H. Rosen, then they follow this notation S composite R for the composition of R and S, and Tremblay and Manohar are using this notation R composite S for the composition of two relations. So depending upon the text which your university or college is using, you have to use appropriate notation, because we know that composition is not a commutative operation. We will see that R composite S and S composite R may be different. They are not always equal. So this operation is not commutative. R composite S and S composite R are not always equal. So be careful, whenever they ask you to find out R composite S, then you should find out both the compositions, or you should find out R composite S as well as S composite R. So they will give full marks whatever notations they are using, according to the notations they are using. And for the time being, we are going to use this notation R composite S for the composition of R and S, and definition is ordered pair XZ belongs to X cross Z such that there exists some element, say small y, in set capital Y such that XY is in relation R and YZ is in relation S. So suppose I am interested in finding the composition of R and S, then in the relation R, suppose I have some element, say X comma Y, then in the relation S I will search for that ordered pair whose first component is Y. So I have to search for all those ordered pairs in relation S whose first component is Y. Suppose here first component is YW, here suppose first component is YZ, then here I have XY, here I have XYW. So XW is a member of R composite S. Similarly here also I have first component as Y. So from these two I have XZ in the composite of R and S. So this is the way how we will decide this composition of two binary relations. Sometimes your relations may be infinite also. So in that case also we will discuss how to write down composition of two binary operations, and we are going to find out composition of binary relations using this notation as well as using these notations, because different authors are using different notations. S composite R is also the notation for the composition of R and S, and this is analogous to the composition of two functions. We know that if f is a function from a to b and g is a function from b to c, then G composite F is a function from A to C, that is composition of F and G. So this notation is analogous to this notation of composition of functions. Therefore, some authors are using this notation for the composition of binary relations and some authors are using R composite S notation. So we are going to follow this notation, but we will find out R composite S as well as S composite R, and we will keep in mind this definition for that composition of two relations. So if they ask you to write down the definition, you should write in this way. This is the definition of composite relation. Let capital R be a relation from a set X to a set Y and S a relation from Y to a set Z. The composite of R and S is the relation consisting of ordered pairs X, Z. In composition of R and S, we will have this type of ordered pairs X, Z satisfying certain condition. So ordered pair X, Z is in composition of R and S if X belongs to capital X, Z belongs to capital Z, and there exists an element Y in set capital Y such that XY belongs to R and YZ belongs to S. That is, second component of this ordered pair is same as the first component of this ordered pair, and from this we find that XZ is a member of composition of R and S. The composite of R and S is denoted by R composite S, and some authors are using S composite R also. And this is definition in the form of set. R composite S consists of all those ordered pairs X, Z in capital X cross Z such that for some Y in capital Y, XY belongs to R and YZ belongs to S. The operation of obtaining R composite S from R and S is called composition of relations. The domain of R composite S is a subset of the domain of R. Domain means the set of all those elements which are first element in the ordered pairs belonging to given relation. So here we can see first elements are nothing but members of relation R. Therefore domain of R composite S is a subset of the domain of R, and range of a relation is nothing but all those members which are second components in the relation. So here Z belongs to this set capital Z. So here range of R composite S is a subset of this range of S. S is a relation from Y to Z. Therefore range of S is a subset of Z, and range of R composite S is a subset of range of S. So here I have taken one example to explain how to find out composite of given relations. So we will find out all these compositions one by one, and here first we have to find out R composite S. So we first write down the definition R composite S. We know that R composite X means XZ, all those ordered pair XZ such that there exists some Y such that XY belongs to R and YZ belongs to capital S. So using this definition we can concentrate on all those ordered pairs in the relation R whose second element is the first element of relation S. First we start with this order pair 1 2, and we will search in relation S for those ordered pairs whose first element is 2. So here we have first element as 2. This is the only order pair in which first element is 2. So we can see here ordered pair 1 2 is in R, and order pair 2 5 is in S. Therefore ordered pair 1 5 belongs to R composite S. So here I will write down first ordered pair as ordered pair 1 comma 5, and there is no other ordered pair whose first component is 2. Now we come to the second ordered pair in relation R. Here second component is 4, so I have to search for those ordered pairs in S whose first component is 4, and this is the only ordered pair having first component as 4. Therefore here we have 3 4 in capital R and 4 2 in capital S. So we can see 3 comma 2 is in R composite S. So here I write second element as 3 comma 2. We can see that for 3 comma 2 there exists this element 4, such that 3 4 belongs to R and 4 2 belongs to S. Therefore 3 2 belongs to R composite S. Now we check for this. Here second component is 2, and this is the ordered pair in S where first component is 2. So these two are same, and we are left with 2 comma 5, that is in R composite S. So here I will write ordered pair 2 comma 5. So it is easy to write down the composition of two binary relations. So we have checked for all the ordered pairs in relation R. What we have to check for each ordered pair in relation R, we have to concentrate on this second component in each ordered pair, and here we have to concentrate on first component of each ordered pair, as I have done here. 2 2 belongs to R and 2 5 belongs to S. Therefore 2 5 belongs to R composite S. So this is nothing but R composite S. Now we search for we find out now S composite R. So I am following this definition, S composite R. So now I have to search for I will concentrate first on the ordered pair in relation S. I am writing S composite R. So I will concentrate in all the ordered pairs of relation S. Because I am writing S composite R, I will start with ordered pairs in relation S. So here ordered pair 4 2 belongs to S, and second component of this ordered pair is 2. So in relation R, I have to search for that ordered pair whose first component is 2. Here first component is 1, here 3, and here first component is 2. So we can see 4 2 belongs to S and 2 2 belongs to R. So these two are common, and we can write that 4 comma 2 belongs to S composite R. So here I have to write ordered pair 4 comma 2, and there is no other ordered pair in relation R whose first component is 2. So I have done for the first ordered pair of relation S, and in this similar way I have to check for each and every ordered pair in relation S, because I am writing now S composite R. So here now I concentrate on this order pair 2 5 belongs to S, second component is 5. So I have to search in relation R whether there is any order pair having first component 5. So there is no order pair in relation R having first component as 5. So now I come here. Here I have 3 1, second component is 1, and here we can see first component is 1. 3 1 belongs to S and 1 2 belongs to R. Therefore 3 2 belongs to S composite R. So here I should write ordered pair 3 2, and there is no other ordered pair having first component as 1. Now here I have 1 3 and first component is 3, and here we can see first component is 3. So we are left with 1 4 in S composite R. 1 3 belongs to S. Here I have 3. Here also I have 3. So 1 3 belongs to S and 3 4 belongs to R. Therefore 1 4 must be in S composite R. So here I write ordered pair 1 4. And I have checked for all the ordered pairs of S 1 3 and 3 4, that is 1 4. So we have written S composite R. Now we have to write R composite S composite R. I have obtained S composite R, and let me write relation R again here. In relation R we have 1 2 3 4 and 2 2. 1 2 3 4 and 2 2. 1 2 3 4 and 2 2, and I have to find out composition of R and S composite R. I have to write down what is composition of these two relations R and S composite R. And here according to our notation, first relation is R here in the composition of these two. So I will start with ordered pairs of relation R. Here 1 2 belongs to R, and I have to search in S composite R for those ordered pairs whose first component is 2. So there is no ordered pair here whose first component is 2. So I come here for second 3 4. Here second component is 4. Here first component is 4. So 3 4 belongs to R and 4 2 belongs to S composite R. Therefore 3 2 belongs to R composite S composite R. Composition of R and S composite R 3 4 and 4 2. Therefore here I should write 3 2, and there is no other ordered pair having first component as 4. Now I check for 2 2, second component 2 here, and there is no ordered pair having first component as 2. So there is only one element in this relation, composition of R and S composite R. Next one is R composite S composite R. So here I have to find out R composite S composite R. This means I have to concentrate on these two, composition of R composite S and R. So R composite S is written first. So I will start with ordered pairs in R composite S, and I will search in the second relation which is here in R. So I start with this ordered pair 1 5 belongs to R composite S, and here I have to search whether there is any ordered pair having first component as 5. So there is no ordered pair having first component as 5. Now I check for this ordered pair 3 2 belongs to R composite S. Second component is 2 here, and I have to search for ordered pair having first component as 2, and we can see there is 2 here. So 3 2 belongs to R composite S, 2 2 belongs to R. Here 3 2 2 2. So we have 3 2 in this relation R composite S composite R. And last one is ordered pair 2 5. So here second component is 5, but there is no order pair in R having first component as 5. So we are finished. Here also we have only one order pair in this composition. And you can see here I am changing the group here. Here I have written S composite R and R outside, and here I have combined R and S in a group and I have written R outside. So we can see that there are chances that composition of functions satisfies associative property, and it is always true. Composition of relations is always associative, and we know that composition of functions is also always associative, so that property is carried out by relations also. And you can observe that commutative property is not satisfied. We can see R composite S and S composite R are both different. Here elements are different. 1 5 is not in S composite R. So we can say that R composite S and S composite R are different. So composition of relations is not commutative as in the case of functions. Next relation we have to search is composite of R with itself, then composite of S with itself. So first we find out composite of R with itself. Here I have relation R, and let me rewrite again because I have to find out composition of R with itself. 1 2 3 4 and 2 2, and I have to write R composite R. So I start with again first pair 1 2, second component is 2, and here this ordered pair has first component 2, 1 2 belongs to R, 2 2 belongs to R, so therefore we have 1 2 belongs to R composite R. Then ordered pair 3 4, second component is 4, and there is no ordered pair having first component as 4. Then 2 comma 2, second component is 2, and here we have first component. So we can see we have 2 comma 2, and we have to be very careful. Make sure that you have checked for each and every order pair. Here 1 2, so I have to search for 2 as a first component. I find out only one pair, so 1 2 belongs to R, 2 and 2 here, so we are having 1 2 here. 3 4, so I have to search for 4 as a first component. There is no ordered pair with 4 as first component. Then for 2 2, there is only one ordered pair with first component as 2, so we have 2 2. So this is R composite R. Similarly, I have to write S composite S. So let me write S again here. S has 4 order pairs 4 2 2 5, 3 1 and 1 3. 4 2 2 5, 3 1 and 1 3. And I have to find out S composite S. Therefore I am writing relation S again so that I can easily decide composition of S with itself. 3 1 and 1 3. So now I am writing S composite S. So I will start with first order pair. I will concentrate on second component here. It is 2. So I will search for all the ordered pairs having first component as 2. There is only one ordered pair whose first component is 2. So 4 2 and 2 5. Therefore 4 5 belongs to S composite S. Then I have to search for 5 as first component. There is no ordered pair here. Then I have to search for that ordered pair having 1 as first component. So this is the ordered pair. 3 1 belongs to S, 1 3 belongs to S. So we have 3 comma 3 belongs to S composite S. then 1 3. So I have to search for 3 as first component. So only one order pair here also. 1 3 belongs to S, 3 1 belongs to S. So we have 1 1 belongs to S composite S. So this is S composite S. And the last one is R composite R. So this we can rewrite as R composite R, or we can rewrite as R composite R. And keep in mind that composition of relations is always associative. Therefore, either we can find out this one or this one, both are always equal. Therefore, they have not used brackets here because we have R here, we have 3 times R. So R composite R, then composite R equal to R composite in the bracket R composite R. Using the associative property of relations, we can use this notation for this type of composition. Composition of R with itself 3 times or 2 times. So we have obtained R composite R here. And we can use either R composite R, or we can use R composite R first and then we can write that composition. So I am writing here R composite R. So first I am writing R here. So I will search for ordered pairs in R. So 1 2 belongs to R and here 2 2 belongs to R. Therefore 1 2 belongs to R composite R. 3 4 belongs to R, but here there is no order pair having first component as 4. 2 2 belongs to R and here we have 2 2 belongs to R. So we have 2 2. And if you wish, you can write in this way also. We can check for both the types. Suppose I am taking R composite R, then also my answer must be same. So if I am writing R composite R first, then I have to start with these ordered pairs. 1 2 belongs to R composite R, and here I have to search for that ordered pair whose first component is 2. So 1 2 belongs to R composite R, 2 2 belongs to R. Therefore we have 1 2 in this relation. And here I have 2 2. Here I have this ordered pair. So we can see either we find out either we consider this type of grouping or this type of grouping. They are always equal, and it is because of associative property of composition of relations. So this is R composite R. And we can use this notation also. We can write R3. R3 means composition of R with itself. Here I have to write 3 times R. So in this way we can decide the composite of relations, and we make the note that composition of relations is not commutative, and composition of relations satisfies associative property. That is, if I have 3 relations, say R, S and P, then these two are always equal. So this is all about this session, and again be careful, some authors are using different notations. They are using R composite S or S composite R for the composite of relations, and we know that composition is not commutative. So whenever you are giving some exam related to this topic, then my suggestion is that you should find out both the relations. If they give you 2 relations, and if they ask you to find out R composite S, then you should find out R composite S as well as S composite R, because different people are using different notations. So there are chances that different colleges are using different notations. So you should find out both the in both the ways. You should use both the notations, and you can use your that common definition that xz belongs to x cross z such that xy belongs to R and yz belongs to S for some y in the set capital Y. Definition is same but notations are different, and here we assume that x is in capital R and x is in capital X and z is in capital Z, and this small y is in capital Y. But if I am using this notation as composite R, then this will change. Instead of xz I have to write z comma x. In that case z belongs to x and x belongs to z. So I hope you understand. If you have any doubts you can ask in comment section. And this is all about this session. We will continue with the problems of composition of operations, composition of relations in upcoming lectures. Thanks for watching.